Okay. Very welcome, everybody. So, I'm Mahdi, and the topic is Curvilinear model of hydraulic structure in open channels. My supervisor is Alistair Worspeak, just same as my twin brother. First, I have a short introduction about the curvilinear method. Then I talk about grid generator and shallow water equation, and finally I show you my result. So, this is the Danube River in Hungary. Here we have a curved river. Because of this curved geometry, we should have curved flow. And I want to simulate this problem. Another thing in this figure is this hydraulic structure. Around of this structure, we have chaotic condition. What is it? It means small changes in the border of flow and particle make particle and flow travel to different way, not to the same way. You can see we have red recirculation zone and a yellow recirculation zone. I want to work on these two recirculation zones. So that was the main goal of this PhD, this curve. Okay. Now, how we can simulate this curved river? One of the best way for this type of problem is curvilinear method. What is it exactly? It means we can map one irregular border in Cartesian system onto a rectangle in a transform system. How? By applying elliptical partial differential equation such as this equation, Poisson equation, or Laplace equation, or Helmholtz equation. We have to rewrite the governing equation for the transform system. By applying the Jacobian transformation or chain rule, we can rewrite the equation. By the way, who used this method for the first time? I should mention NASA scientists developed this theory for simulating different part of shutter. They call it boundary fitted system. So we know about the governing equation. Governing equation is Poisson equation. We can work on the border of the geometry. But for having the final shape, we should produce the interior lines and interior grids. Then NASA scientists proposed the iterative method. We have different types of iterative method. We have successive over relaxation, multi-grid method, and conjugate gradient. They applied the first one, SOR, a little bit old technique for iterative method. By the way, quick definition about the iterative method. It means after each iteration, the result should become better, more accurate, and we should have less error than previous step or iteration. One Russian scientist developed a multi-grid method, and again one professor from Harvard University proposed the conjugate gradient method. Both conjugate gradient and multi-grid is much more accurate than first one as well. So by applying curvilinear idea and iterative method, we can map this circle, this irregular boundary onto a rectangle. We can do the same thing for multi-grid and conjugate gradient. That was just the geometry of channel. Now how I should analyze the flow feature. We have different type of hydrodynamic equation. Here I chose shallow water equation. This equation is derived from Navier-Stokes equation and includes three main equations: continuity equation, momentum equation x direction, and momentum equation in y direction. Based on continuity equation, we can find about the head of water in channel. Based on momentum equation x and y direction, we can understand about the velocity in channel in x and y direction. That was shallow water equation in Cartesian system. Because we should work with transport system, we should rewrite the equation for transform system by applying Jacobian transformation. So this is my hydrodynamic equation. Now I want to show you some test case. The first test case is the recirculation zone of channel with sidewall expansion. Here, the length of channel is 18 meters, and the width of channel is 2 meters before the step or sidewall expansion, and then the length of channel becomes 3 meters after the step. By moving particle and flow to the downstream of channel, we should have one recirculation zone here, and I want to simulate it. So we can map the physical domain onto a transform domain, and here I work with two Reynolds number. Quick definition about Reynolds number, because we have the IES, but people maybe do not have background about fluid mechanics. But Reynolds, we have different type of fluid. We have laminar fluid, turbulent fluid, and transient fluid. If the range of Reynolds number in channel, in open channel, is less than 500, we know this fluid as a laminar fluid. So I picked two Reynolds number, 98 and 229, as a laminar fluid. Basically, for this type of channel with sidewall expansion, we should have parabolic velocity distribution. And the fluid is entered from this side of channel. Now I want to check my simulation to see do I have any energy losses in program or not. The maximum of the maximum velocity in this channel for the first Reynolds number should be somewhere here, about 1 meter over second. If we draw the time velocity graph at the end of simulation, the maximum of velocity should become the same as the velocity at the beginning of simulation. So we have a 1 meter over second at the end of simulation. It shows we do not have any energy losses in this simulation, and the program is working. We can compare this numerical method with one analytical solution, and we can find out the analytical method for the maximum velocity. And the result is the same as numerical simulation. So the program is working. Let's see the recirculation zone. Here, blue vector is velocity vectors, and colorful lines is string function contours. For the first Reynolds number, it's 98. For the second Reynolds number, we have a bigger step, and we have different type of vortex. This one is the 3D view from, this is the same shape, but from 3D view, and this is the velocity, the string function profile, and you can compare these two figures together. And you can see a string function contours here too. Anyway, that was my first test case for today. Then my second test case is fluid structure interaction. If you remember the Danube River in first slide, we have one structure in river. Before the structure, we should have fluid structure interaction. And after the structure, because of chaotic condition, we should have kind of vortex. And I want to simulate it. So you can see we can generate the grids based on conjugate Curvilinear method or multi-grid. Here again, I use two Reynolds number, 98 and 229. And we can do the same analysis for maximum of velocity, and we do not have any energy losses for this program. So let's see the result. For this problem, time has a key rules. What is it exactly? It means we should have a steady state condition to analyze the whole things. But here I work with two time, 40 seconds and 80 seconds. For 40 seconds, we do not have a steady state condition. But you can see the vortex much better than after the steady state condition. You can see for 80 seconds, when we have a steady state condition, the length of recirculation will become longer than before. And this is a main result. And this one is more important. But it's really interesting to see the effect of time for producing the vortex. And you can see a stream function profile. That was first Reynolds. But for the second Reynolds number, we have different type of vortex. Again, for 40 seconds, you can see the vorticity feature better than 80 seconds, but the main result is 80 seconds. Now, that was my two test case for today. Now, I want to talk about my main goal of this PhD. This is the Danube River. The river is started from here, Black Forest in Germany. After through passing, I think, 10 countries, river reaches here, Black Sea. The length of river is about 2,000 kilometers. But why we should work on this river? Because of flood. Let's look at one flood in 2002. The impact of this flood was so deep and tragic, more than, I think, 20 billion pound damages across the Danube. And I think 80 people died and lost their life to this flood. The first picture belongs to the March before the flood. And you can see the situation of the curved border of Danube River. And the second picture belongs to April after the flood. And you can see what a bad condition we have for curved border. Let's look at another picture from city of Vag. This city is close to the Budapest, I think 50 kilometers from Budapest, the capital of Hungary. We can see the situation of city before the flood in March, and another picture belongs to International Space Station, and you can see what about condition we have for farmland and city. What is the solution? How we can fix it? We can train the river against the flood by adding flood protection system. We have different type of flood protection system. We have check structure, different kind of gates, drop structures. But the most important structure for Danube is groin and dikes. Because we have an import and export industry, so we cannot use so many structures in this river. We have twist industry. So engineers should pick the economic flood protection system, and they should see the impact of this flood protection system on the economic too. So they pick groins as a best one. We can put this type of flood protection for each bank separately. We can add it into the left bank of river or right bank or for both bank. So let's look at just the first curve. Here I work with 90-degree curve. Here we have one inlet, the length of inlet 2 kilometers. Then inlet is attached to the curved part, and again we have outlet. The length of outlet is the same as the inlet, 2 kilometers. By applying curvilinear method, we can map this border onto this line onto this line, this line onto this line, and finally this line onto this line. Then we should use iterative method to produce interior grids. We can use multi-grid to generate the grids. So this is the geometry of river. Then I use shallow water equation to analyze the flow feature. And you can see velocity vectors based on shallow water equation. We can compare our result based on analytical simulation, and you can see we have they both are in good agreement with each other. And you can see a stream function contours. Stream function profile and velocity profile. Here, velocity profile has a parabolic profile, and because a stream function is derived from velocity, so second order equation become first order equation, and we have a linear type of profile for a stream function. Now we add the flood protection system, and before we do not have, when we do not have any flood protection system, the maximum of velocity is about 1 meter over second. By adding, I add 4 groins to the curve part. The velocity, we can reduce the velocity by this action, and it becomes about 0.7 meter over second. And we can check our result at inlet and outlet, and we have exactly the same value for velocity, and we do not have any energy losses for our simulation. That was the first curve. The second curve belongs to city of WAG and 180 degrees. It's the same simulation, we just change the degree. Instead of 90 degrees, we have 180 degrees, and you can see the velocity vectors, the stream function contours, and velocity profile, and the stream function profile. And finally, we add the groin to support each bank separately. Anyway, if you ask me what is your plan for future, currently I want to work on particle tracking around the structure. You know, sediment are trapped around the structure, and I want to track them. Unfortunately, the result is not ready yet. Hopefully, I will add it till December. Just I want to introduce the methodology of particle tracking. So here we have one rectangular tank. At the center of this tank, we have one vortex, and based on this equation. Now imagine we want to track one particle everywhere we want, for example this point. First we should find this point in this geometry. It should find a specific cell. This point belongs, for example, to this cell. So we know everything about this cell. We know velocity at each coordinate. Based on linear interpolation, we can find about the velocity for this specific particle. And then we can track the path taken by particle based on time integration method. You know, because velocity and displacement and time has a relationship. And you can see the particle was here at the beginning of simulation, and you can see the circular shape for particle tank. Now let's look at another test. Here I want to track the particle based on chaotic motion. For providing chaotic motion, I pick 2 vortex instead of 1 vortex. For the first half period, the first vortex, the right vortex is on, and the left vortex is off. And for the second half period, the left vortex is on and right vortex is off. And I want to track 15 particles. We have 6 particles on x-axis, 9 particles on y-axis. I track the particle for 500 periods. So you can see 500 multiple 15 points. You can see here is about 7,500 particles based on linear, linear interpolation, particle tracking. The dynamic behavior of particle depends on this term mu. If we change it and pick it the big value, you can see the chaotic motion better. You can see for this one, chaotic motion better for 0.2. And finally, the entire particle completely become homogenized for 1 or 1.5. We can change the experiment. Instead of 15 particles, we can put the patch of particle at the center of 2 vortex. If you remember, for 1 second, the right vortex is on, so particle travel to this way. For the time second, this one should be 2. The left vortex is on and particle travel to the left side. Now time is 3. And you can see chaotic motion is started. Time 4, 5, 6, and 9. And finally, the particle completely become homogenized at time 12. So hopefully I will work on Danube River based on linear interpolation particle tracking, and for conclusion I talk about curvilinear method and iterative technique. Then I talk about shallow water equation and show you some test cases, and finally I talk about the particle tracking. Thank you guys.
This production is brought to you by the University of Edinburgh.